Thank you very much. And well, actually, I suppose I should say something because I see on the screen that somebody from my group, Sylvia, just switched on her video and she's boarding a bus, listening to the talk. So hello, Sylvia. I suppose you also see her.
I don't know what happened, Danuta. So I get out immediately.
Okay. Well, the idea for the lecture today started with the project identified, coordinated by David Lurie. It was the project finished actually at the end of the first year. The idea, there were a lot of ideas. However, the underlying idea was somehow whether one could exploit fast field cycling, or generally saying low field, to increase the capability of NMR methods to detect diseases. So the first question was, what is the difference between relaxation for healthy and pathological tissues and whether one sees any? And if so, why? Already you know that one does see a lot of differences, and actually I will have a very interesting lecture about that. However, we are responsible for the work package, which was more or less referred as studying model systems. So, okay, we started with model systems. For model systems, we thought that actually proteins are perfect model systems. Actually, well, people study proteins using high field NMR. So you can imagine, when you just start talking about how to say that you will perform low field studies of proteins, then immediately, of course, the question is, but we will not define any structure, actually the structure is already known. Then you start explaining that you would like to get some information about dynamics, but then, of course, the reviewer might ask what is just interesting about dynamics. So this is a kind of difficult problem. However, no, okay, we started with proteins. So as you could see here, there's 4 examples of proteins, different ones. The abbreviations are quite obvious, and the spectra collected, yeah, in principle, like 35 degrees. Yeah, so more or less about body temperature, but you will see that this is not important at all, actually, at least in some temperature range. And the proteins were supposed to be dry. Of course, to which extent? As much as possible, I would say. They were bought as powder, lyophilized powder, and we tried to keep them dry. And the relaxation dispersion profiles. The first, how to say, somewhat disappointing information is that actually all the relaxation data are very much similar. We have different proteins, however, well, all of them just start between 1000 and 2000. All of them just end somewhere here. Okay, for elastin, there is something here, but it is really hard to build a story upon that. In fact, they are almost the same data. Actually, one should be aware that we do not see any water here because in principle there's no water in those samples. So you really see protein dynamics. Actually, okay, even if one asks whether it was some water, I can answer, okay, if we have, I don't know, 0.05% of water, of course you cannot see water in such experiment. You can ask to which question the water affects the dynamics of the proteins. But this is a different question. It's somehow obvious that the signal comes from the protons of those proteins. So, okay, they are similar. And in addition, you see something which is called quadrupole relaxation enhancement of the quadrupole peaks. This is actually not surprising. However, I will say a couple of things about the quadrupole peaks in a second. However, it might, because usually, for instance, when one looks at tissues or just some partially hydrated proteins or some biological systems, there is a concept that actually We know that such effects are seen if the dynamics is slow. So there is a concept that there is a slow exchange of water molecules, which is responsible for creating those peaks, which actually cannot be like that because we do not have water here. So somehow it's obvious that those quadrupolar peaks stems just from protons of the proteins. There are, of course, also several ideas what it might be. NH2 groups, yeah, because I will say in a second, actually, in more detail, that actually, okay, maybe I should say it now, that actually general argument has two contributions to proton relaxation in proteins. It's proton-proton dipole-dipole coupling and proton-nitrogen dipole-dipole coupling. And those so-called quadrupolar peaks stem from proton-nitrogen dipole-dipole coupling. This is dipole-dipole coupling, for sure. However, they appear because nitrogen is P1, and therefore it shows quadrupolar coupling placed in external magnetic field. However, it's somehow obvious that those effect, which is quite pronounced here, is just internal part of the relaxation of protons, dry protons. No, okay, so it is like this. Then one can interpret it, or maybe one should put it in this way. Whether one can, this is just a question. Well, there's a lot of models, as usually, how to interpret NMR relaxation data. For sure, almost all of you, I suppose, know that in case of solid proteins or weakly, how to say, hydrated proteins, one looks at slopes, so-called relaxation slopes. So there is logarithmic scale here, like in this figure, logarithmic scale in the frequency axis, and those data are supposed to show a slope. I mean, the dependence should be linear with a certain slope. The fact is that if you look at that just at this moment, you might get the impression that it is indeed a kind of straight line in this representation. But if you would like to draw a line, you will see that it's not in fact. This is one thing. Second thing is actually personal. I would say that I do not like relaxation slopes. It's not that I do not believe in this theory. However, it's somehow a way to get knowing more. I mean, slopes can be okay, and I can agree with slopes. However, first let me try something else. Okay, this is this kind of approach. So, but the something else is not really very original. Because what we have done here is just, as I said, we have proton-proton and proton-nitrogen relaxation contributions. So, as far as proton-proton relaxation contributions are concerned, we just more or less decompose the contribution into three processes plus a constant. So just three Lorentzian processes. It's not really original, and one can say in principle, but you see, if you would have decomposed them into 5, you will get even better. Okay, I'm saying I got a very nice one. However, of course, it does not make much sense, and it's hard to say when to stop. I mean, okay, I might trust in such a decomposition if it will include 2 processes plus a constant. Well, in this case, we needed 3. However, I said, if you just decompose a function into, I don't know, power series, Fourier transform, and so on, there's some information in that. So let us, how to say, not thinking much about what is behind, try to decompose the proton-proton contributions into 3 terms, which we just refer as slow, intermediate, and fast one. I mean, in terms of the correlation types, because there is dynamics associated with each term. And because one can expect that the correlation times will be different, so one can call the correlation times slow, intermediate, and fast, yeah, because there are 3 of them. Okay. So if you apply this approach, you will get three contributions. This green one is associated with the slow process. This orange one is the intermediate one. This one is the fast one, plus you have the constant. And now you have proton-nitrogen contribution. This is the purity line. And actually here we applied a model which has several limitations from one side. However, from the other side is just something which is perfect, because in some cases, and for sure for solid proteins, I can discuss the assumption later, it can really be used to describe the proton-nitrogen relaxation contribution and the shape of the quadrupole peaks. Actually, this equation also for high-speed quantum number, not only one, was delivered by Pascal Brice. And it's pity that that somehow this concept is not exploited more. I will come to the details of this subject later. Now it's somehow, you agree that it fits, yeah? So, okay. Okay, one can collect parameters. Usually I try not to show tables, and I will not be talking much about the parameters now. I will come to them also later. However, of course, if you perform this kind of feats, you get parameters. So you have the amplitude, the dipole relaxation constant, the correlation time, next constant, next time, next constant, next time, the coupling, the frequency independent term L. Then from the position of the quadrupole peaks, you get quadrupole coupling constant and so-called asymmetric parameter. We can come to this point now. It's like that. If there is dipole-dipole coupling between proton and nitrogen, and the dynamics is quite slow, I mean so slow that it does not average out the quadrupole interaction of the nitrogen. However, fast enough so it averages out the proton-nitrogen dipole-dipole interaction, which is actually very easy because the geomagnetic factor of nitrogen is quite low. So proton-nitrogen dipole-dipole coupling is not very high. However, if the dynamics is low enough, so let's say the product of the quadrupole coupling of nitrogen times the correlation time, which is responsive for the fluctuation of the quadrupole interaction, what is that is another story, is larger than 1, one can say that actually the energy level structure of nitrogen is not only determined by the Zeeman interaction, but also, or even most, by the quadrupole interaction of nitrogen. Therefore, at some magnetic fields, the proton-Larmor frequency will match one of the nitrogen transition frequencies between its energy levels. Nitrogen has the spin quantum number 1, so there are 3 possible energy levels, and it means there are 3 transitions between the nitrogen energy levels. So there are 3 frequency-specific relaxation maxima, and they correspond to the situation when the proton resonance frequency matches one of the transitions of the nitrogen. And one says then that actually, if such matching occurs, the proton magnetization is sometimes taken over by nitrogen, and then the proton magnetization disappears faster, and then it manifests itself as a frequency-specific relaxation enhancement, proton relaxation enhancement. The problem of quadrupole peaks is just a separated subject. I will see whether there is a chance that I could talk a little bit about that. However, the trick is that The first one appears at a frequency which corresponds to the difference between those two ones. Okay. And what it includes? It includes some angles which describes the orientation of the proton-nitrogen dipole-dipole axis with respect to the principal axis system of the electric field gradient at the position of the nitrogen nucleus. So it's somehow related to the geometry. There's the amplitude, proton-nitrogen dipole-dipole coupling, which includes the proton-nitrogen distance, power 6, by the way. And there's a correlation time, tau Q here, which in the original formulation of Pascal was just the rotational correlation time. However, here it's again not going into much details. It's again a correlation time which characterizes the fluctuations of the quadrupole interaction. That's it. So with those parameters, yeah, from the position you just calculate the quadrupolar coupling constant and the asymmetry parameter. One calculates the geometrical parameters. One can calculate the proton-nitrogen dipole-dipole coupling, and one should, but I do not do it at this moment, convert it to the distance between proton and nitrogen. Then there is the time, which, as you could see, more or less is somewhat shorter than the correlation time tau s. Yeah, in this decomposition. In principle, by brute force, one could keep it equal to that time. And the fit will be not much worse. Now, okay. Then something about the quadrupole parameters and the quadrupole relaxation enhancement. Before I will continue with proteins. I said that this equation is so great and of so much use. Yes. You see, here is a kind of thing. Here we compared predictions of the relaxation delivered in that paper, the relaxation equation delivered in that paper, which has a very simple mathematical form, with something which we call general approach to the quadrupole relaxation enhancement. For sure, remember the lecture of Joseph. He was talking about paramagnetic relaxation enhancement and so-called Swedish slow motion theory or Stockholm slow motion theory, when somehow one solves fully the Liouville equation to get paramagnetic relaxation enhancement. You see, there's in fact no difference between zero-field splitting for electrons and quadrupole coupling for nuclei. So mathematically, one could relatively easily adapt the so-called slow motion theory, which was supposed to describe paramagnetic relaxation enhancement, is not only supposed it does in an excellent way, to describe quadrupole relaxation enhancement. And this we have done. And actually, here, this X is the amplitude of the quadrupole coupling times the correlation time. Below 1, nothing is happening. There's no quadrupole relaxation enhancement. And the equation, just this analytical form here, will also predict no quadrupole relaxation enhancement. Then this product increases. It means the dynamics becomes slower, and slower. And here you have a comparison between the equation, between the predictions of that equation and predictions of the quadrupole relaxation enhancement based on, so how to say, fancy calculations like here, using stochastic Liouville equation. I call it the beauty of quantum mechanics. I'll tell you why. And you see, actually, the solid lines stem from that equation. The dot lines stem from this general approach. And you can see that they agree when there's almost no enhancement, what is okay. And they agree when the dynamics is very slow. However, in the intermediate range, not really. However, this is okay, again, as long as one is aware of those limitations. One can explain the discrepancies referring to the validity range of this analytical equation, but this is not the main part. Actually, at this moment, I would like still to say that it was a time when we were writing a kind of special issue for molecular physics related to the cost action, and we published there a paper. It actually referred to bismuth because bismuth has some high spin quantum number, and it was a lot of quadrupolar effects then, discussing just different notional regimes, until which condition one should call it relaxation enhancement, until which polarization transfer, when under which conditions such effects can appear in the quadrupolar peaks. It just discussed really in many details. And coming back to proteins, here you see that actually using this model, so this analytical model, and it in this case gives very nice agreement with the general one. We can really very nicely reproduce the shape and the amplitude also of the quadrupolar peaks. So what I want to say that if you look at that, it's not only that this is because of the scale and one does not see details. If you enlarge things, this also looks nice. So somehow we have many parameters, however, we reproduce the data very nicely. Probably not surprising. But then, let us continue with the studies. So we had actually different proteins, but the temperature was almost the same, yeah, plus minus 1 degree. So in this case, continuing further, we decided to change temperature. We also incorporated myoglobin to the studies, and actually the conclusion is more or less the same. Even if you change temperature, the relaxation dispersion data are almost the same from type proteins. The difference is actually that for myoglobin, you do not see quadruple relaxation enhancement, but this is related to the fact that there's iron there, and iron is paramagnetic. And somehow the nitrogen is also coupled to iron. So this coupling is strong and it enhances the nitrogen relaxation, and therefore the quadruple coupling is averaged out. So the presence of paramagnetic species is responsible for the disappearance of the quadruple peaks here. However, the shape is still the same. Okay. Well, so what to do now? Actually, so far it's not really very interesting, because we decompose those data into those Lorentzian functions. We show that we can very nicely reproduce the quadrupolar peaks. But can one really believe in that? So, okay, so we decided to compare the results with dielectric spectroscopy results, which were supposed to give information about molecular reorientation. However, before that, one must become more familiar with so-called substituted representation of relaxation data. And I couldn't stop myself from saying here that I strongly dislike this concept. Actually, why? There are two reasons for that. One is not very rational. However, it's like that. We collect the curves, yeah, relaxation, dispersion data, and we just like them in this form, that are flat at low fields, and so on and so on. And being asked to present them in a different representation is very no, spoiling them. What for should I present them in different representation? But this is, I would say, personal opinion. if we would try to talk with people who are present by dielectric spectroscopy and would ask them to divide the so-called susceptibility curves if they measure in dielectric spectroscopy by the frequency to get curves similar to ours, they will probably also protest. However, here we have to somehow agree that we should go to the susceptibility representation because otherwise we will not be able to compare NMR with dielectric spectroscopy. So, how this is done? We have the relaxation curves. They are just simulated curves. And we multiply each of the curves with the resonance frequency. So, on x-axis, I keep resonance frequency. On y-axis, I have relaxation rate times the resonance frequency. So I get things like that. Then in the ideal case, when actually there's no new mechanism of motion, nothing changes, only the time scale of the motion changes with temperature, because one could imagine here that actually faster and faster motion means higher and higher temperature. However, the theoretical model is all the time the same. In principle, if one goes to the susceptibility representation and gets such curves, then one can somehow put them together, shifting them just along x-axis. You see, it stems from the fact that a lot of relaxation expressions, when you multiply them with omega, with the resonance frequency, becomes dependent not on the correlation time in the frequency separately, but in all the relaxation formula, it will be correlation times the resonance frequency. So in principle, this more or less says that you get the same relaxation rate at that for shorter correlation time, you get certain relaxation rate, and you would get the same relaxation rate for longer correlation time, however, at lower frequency. So the product omega tau is the same. And if such curves overlap, one sometimes calls them master curve. Okay. The second reason why I do not like it, it's somehow that if I take, how to say, this well-known formula, j omega plus 4 j2 omega, with, how to say, Lorentzian functions, spectral densities. It's somehow obvious what happens if I multiply them with omega. I will get omega tau divided by 1 plus omega tau squared. Yeah. So one can play this again. However, if we have more, actually, nuclear magnetic resonance is a quantum effect, and the relaxation is just quantum effect itself also. And one is not, the dynamics is one part of that, but the quantum mechanical scenario, all possible spin interactions and so on, is the second part of the relaxation theory. So for instance, you can say, yeah, like so two identical spins, you have this j omega plus 4 j2 omega, then you can ask what is actually omega. You can say, okay, it's simple rotation, exponential correlation function, you will have exponential spectral density. But then if I have, for instance, proton fluorocopying, it will be not j omega plus 4 j2 omega, but it will be, if I remember it good, 3j omega fluor minus omega hydrogen, another way around, does not matter, plus 3 times j at omega hydrogen, plus 6 times j omega hydrogen plus omega fluor. So the relaxation expression itself will be different because of quantum mechanics. Then we can again ask what will be the motional model, so which form the spectral density will take. However, just for systems including quadrupole nuclei, paramagnetic nuclei, just magnetic nanoparticles, for interactions which depends on the magnetic field, like for instance, G-tensor anisotropy. Really, one can get a strange shape when one just makes this kind of representation, and then one can somehow mislead it with different notional contribution, not quantum mechanics. However, well, such a concept does exist, and we have to use it to compare data. So now we use the same temperature which we did for NMR Relaxometry, and still quite protein, and we perform dielectric spectroscopy studies. Here we have also big ones. I will not be going much into the details of dielectric spectroscopy studies. However, usually you see a kind of long tail here. Whatever. If you want, I can explain it in more details, but there's no time. What we have done here, we just rescale the spectrum in such a way, so if the data show maximum, the maximum is 1. Yeah, that's it. I just purely rescale. However, in this way, you can better see those maxima, and actually it's similar to that. Yeah. Now, okay. So, with those results, let me make such a thing. This is for LS. So those data, you can look actually at one temperature. Those points are dielectric spectroscopy data. Yeah, this one, actually. Okay. Then what I can do? You remember, we have those 3 processes, fast, intermediate, and slow one, which we use to decompose the relaxation dispersion data for protons. So I can use the correlation times. And I can keep the proportion of those contributions according to the proportions of the relaxation, of the dipolar relaxation constant. It does not make much explanation. However, this is the first act. So I just take those 3 contributions, fast, intermediate, and slow one, from the decomposition of the NMR data. I present them in the susceptibility representation, and keeping, how to say, the ratio between the 3 factors, it means the dipolar relaxation constant, I just gave them to 1. You see, this is a fantastic agreement. This is also one thing, if somebody would like to remind me. I'm aware that the correlation times for dielectric spectroscopy is 3 times longer than for NMR, because in case of dielectric spectroscopy, we have like 1 correlation function, and for NMR, like 2 correlation functions, so this is taken into account. The agreement is not bad. This is the solid one. Yeah. Okay. Then I could do something else. Just interpret the dielectric spectra, forgetting about NMR. Actually, to interpret dielectric spectra, people quite often use this. It should be the composition, sorry. People just quite often use this so-called Davidson function. It's a phenomenological function. Unfortunately, in my opinion, it becomes more and more popular in NMR, but this is a completely different subject. However, I could interpret the dielectric spectra in such a way, like how to say dielectric people would like. And then one can figure out that actually this peak can be reproduced with 2 contributions, not 3. However, you have 1 more parameter. This is a kind of distribution of correlation time, this beta so-called here, which makes this straight here. In addition, there's a kind of very slow process which I observed here. Okay. However, independently of that, one could think, actually, I could easily improve this figure. Because why should I keep in dielectric spectroscopy the same ratio between the contributions that in NMR? In NMR, there are dipole-dipole interactions, and there's the distance between protons, and there's the power 6 of that, so it's very sensitive to that. Here, the contributions are just limited by components of electric moment, electric dipole-dipole moment. So really, I should rather look only at the correlation times. And I should be free to play with the amplitude of those contributions. And if you do that, you can very nicely reproduce the dielectric spectrum. So it gives you something to think about. Because actually, maybe it's not only a kind of decomposition, which is artificial. Maybe those processes really do exist because it seems that they are confirmed by dielectric spectroscopy. Okay, let us do it again for some other. Actually, again, if you just do it for myoglobin, using the ratio between the dipole, between the contributions, following the ratio between the dipolar relaxation constant, well, you are off. But definitely you see that this is not hopeless, yeah, because actually the peaks are in the right positions. So if you adjust the ratio, you can again very nicely reproduce the dielectric spectroscopy. It is, so one could say, welding the composition just as a kind of physical foundation. Too nice to be true. Look like Robinson argued. Whatever you do here, there's no way with those peaks, whatever amplitude I will take here, to get a maximum here. Why? I don't know. However, this is the result of the comparison. Let us go further. Let us add some water. So you have slightly vibrating body elastic. Well, nothing really happened. You see, still, the data are pretty much the same. You can say the vibration level is low. Okay, you still see quadrupole peaks. And it also not very sensitive to temperature. Let us add more water. You see, here is somehow obvious, but because we have only 10% of vibration, we measure, how to say, signal from protons, from proteins. Here, if one would like to say that not necessarily, because actually we have almost 40% of water, I would say that it does not differ much from the previous one. So somehow we still measure signal from the protein. Okay. Then one could, for instance, take something else, Robinson albumin. One can change the hydration level. Yeah, one can compare. One can compare just the dry one with slightly hydrated one. Actually, in this case, it seems that the the fast motion becomes faster when you add some water. You can create some gels. Eventually, you can measure relaxation data for highly diluted compounds when definitely then you get signal from water. Yeah, you can get through all that and see how this evolves. Actually, one should be very careful, in my opinion, because I just do not think that the relaxation will be exponential. However, I think, I mean, in this sense that, okay, another way around. If you, for instance, take 40% of water, yeah, for this case, you have 37 here, and the signal from protein was measured. Divided 40% here, and they get such a line, which merely corresponds to this level. There is the question whether the experiment was not set in such a way so one just measures only water. Because the process, yeah, can be like that here. But for instance, there is a fast component and a slow component. And actually, I don't know if the experiment was set like that. One measured just only the slow component. It is nothing wrong in that. But I think think that somehow it shows us that maybe it's not true that in the solutions one can measure only water. That maybe one could really catch also the macromolecular approach. Actually, here it's to say if one would be interested how the quadrupolar peaks evolve with when the dynamics changes. It's a kind of figure. Yeah, for fast dynamics they are not there. For slow dynamics, there's the correlation time change by the order of magnitude are well pronounced. Okay. Then, with this knowledge, let us come to tissues. They are the last two slides. I will not repeat what Lionel said. However, what we have done here, a lot of relaxation data for healthy and pathological tissue, and for sarcoma tissue and muscular tissue, healthy tissue. We played some tricks to group them into individual groups and try to correlate it with histopathology and so on. Actually, Lionel had already lectured about whether the data differ, whether not, whether one can detect cancer in this way. This is a separated subject. But you see that we just, there are also slight effect of the quadruple peaks, and you have fits here. What we have done, we have just decomposed the data for tissues also into three contributions, plus this proton nitrogen part. And take, this is what I can for the rest. You see, not going much into details, but here we have the correlation time for proteins, -6, -7, let's say -8. Yeah. Well, -6, -7, -8. So somehow, if you decompose the relaxation data for tissues into such a way, you get a correlation times which are similar to those for solid proteins. The fact that the data look differently is because of the different dipolar relaxation constants and different proportions between them. Because actually you can say, you had for protons just for proteins, very steep curve, and actually you have flat curve for tissues. I would say you see that in specific, even the correlation times are the same. Because actually I have always the fast process, yeah? And in the fast process with a large dipolar relaxation constant in front, well, the curves will be rather smooth. If, how to say, the dipolar relaxation constant for the slowest process will prevail, the curve will be quite steep. However, I don't know whether this is surprising or not, but it might be worth noticing. Then I will just finish with this, how to say, observation, let's put it in this way. What we really measure, what we see in the sense that what is the meaning of those emotional processes, those relaxation contributions, which are, how to say, not artificial, not only to decompose the data, in my opinion, because they are also revealed in dielectric spectroscopy studies. In some cases, the correlation times agree, in some they do not agree, but well, there's something in that. And what one can learn from comparing just parameters for so simple systems like proteins and tissues. So, well, I want to thank to identify. This is obvious. I want to thank to cost. I would also like to thank to people who are well involved in this work. Elżbieta, Małgorzata, Miłosz, Paweł. All of them participated in identifying. And of course, David and Leon. And very much thank you all. I hope it was not very boring. So I finished.